All right, let's talk about a word you hear everywhere these days: algorithm, right? It's in your social media feed, it's in your GPS. I mean, it's kind of running the world. But what is one, really? Let's figure it out together, step by step. So let's just dive right in. What is an algorithm, anyway? Okay, so if you look it up in a computer science textbook, you'll get this definition. But, that sounds a little dry, a little abstract, doesn't it? The truth is, you and we use algorithms all the time, every single day, without even thinking about it. No computer needed. Don't believe me? Okay, let's try a little thought experiment. Picture this. You walk into a room. How do you figure out how many people are in there? What's your method? I bet the first thing that pops into your head is you just point at each person and count, right? 1, 2, 3, 4. And boom, just like that, you've created and used an algorithm. Seriously, it's that simple. Okay, now let's nerd out just a little bit. In the world of coding, you often sketch out the plan in something called pseudocode. Think of it like a recipe, but for a computer. It's plain English that lays out the steps. For our little counting method, it would look something like this. So what are we even looking at here? Well, that first line, let n equals 0. N is just our counter. It's a placeholder for our number. And we start it at 0, which makes total sense, right? Before you start counting, the count is 0. Then the second line. That's a loop. It's a command that just says, hey, do this next thing over and over again. And what's the thing? For every person you see, add 1 to n. All right, so we've got our instructions. We've got our little algorithm. But here's the million-dollar question in programming. Does it actually work? I mean, does it work every single time? Let's try and break it. Let's, as they say, bang on it a bit and see if it holds up. Let's run a test. Say there are 2 people in the room. N starts at 0. We see the first person, boop, n is now 1. We see the second person, boop, n is now 2. No more people, final answer, 2. Perfect. But what about the weird situations, what programmers call corner cases? Like, what if the room is empty? Well, n starts at 0, the loop looks for people, finds none, so it never even runs. The final answer is 0, also correct. Okay, this thing seems pretty solid. So it works, it's correct. We could stop there. But in the world of algorithms, correct is just the price of admission. The real game is asking, can we do better? Can we make it more efficient? Can we make it faster? What if instead of counting every single person, what if we paired them up? We could just count the pairs and go by twos. 2, 4, 6, 8. It just feels faster, doesn't it? Seems like it would take half the time. And look at how small the change is in our pseudocode. All we're doing is swapping out n plus 1 for n plus 2. One tiny little change to the instructions, but it completely changes how we're approaching the problem. We're going from slow and steady to twice as fast. All right, let's put our new speedy algorithm to the test. Let's use our same test cases. 2 people? That's 1 pair. N becomes 2. Check. 0 people? That's 0 pairs. N stays at 0. Check. See? So far, so good. It looks like we've made a brilliant improvement. But what about the one we didn't test? What happens when the number isn't even? This is where things get interesting. What if there were 3 people in the room? Okay, let's walk through it. N starts at 0. We see a pair of people, so we add 2. N is now 2. Great. But wait, there's still 1 person standing there. Our rule is to look for pairs, and that person isn't a pair. So what does our algorithm do? Nothing. It just stops. So it gives us the final answer, 2, which is just wrong. There are 3 people there. We can see them. And right there, that mistake, that's what a programmer would call a bug. It's a flaw in the logic, a mistake in the recipe that gives you the wrong outcome. Our faster algorithm isn't so great now, is it? It might be quick, but it's not correct, and correct is what matters most. So back to the drawing board. How do we fix this? The problem is pretty clear, right? Our algorithm is great with pairs, but it totally chokes when there's a single person left over. We just need to give it one more instruction, a way to handle the odd one out. And here it is, the final, perfected version. We keep the first part, counting by pairs, but we add a brand new line. A simple but powerful instruction. If there's 1 person left over, then just add 1 to the final count. That little if statement, that's the real hero here. It's what's called a condition. It's like a special rule that only kicks in when it's needed. only when it sees that lone, unpaired person. And with that one little addition, our algorithm is now both fast and correct. It's robust. It'll work for any number of people you throw at it. And this whole process we just went through, that is what creating algorithms is all about. It's not about being perfect the first time. It's about defining the steps, trying to break them, finding the bugs, and then refining and improving your instructions until you have something that's really, really good. It's a cycle of building, testing, and fixing. So at the end of the day, an algorithm is just a fancy word for a set of steps to solve a problem, whether it's the steps to make a cake, the steps your GPS takes to find the best route, or the steps to count people in a room. And that really just leaves one question, doesn't it? If you could design a set of steps to solve any problem, what problem would you solve?